Something is holding the largest structures in the universe together, and no one can find what it is. The universe, at the scales humans can observe, is not smooth. Matter does not spread evenly across space. Instead, galaxies cluster along thin, curving threads, forming massive filaments that stretch across hundreds of millions of light years. Between these filaments lie enormous voids, regions nearly empty of galaxies, of gas, of visible matter. The filaments connect at dense nodes where galaxy clusters accumulate. This is the architecture of the universe at its largest scale. It has a name: the cosmic web. For decades, cosmologists have worked to explain how this structure came to exist. The models begin with the early universe, a near-uniform distribution of matter, seeded with small density fluctuations. Gravity over billions of years would amplify those fluctuations. Dense regions would pull matter inward. Less dense regions would empty out. Over time, a web-like pattern would emerge, consistent with what is observed. In principle, the explanation is clean. In practice, something does not add up. The cosmic web is not merely large. It is organized in a way that pushes against what the underlying data can support. The filaments are too coherent. The voids are too defined. The nodes too concentrated. When measurements of the actual distribution of matter, visible matter, dark matter included, are fed into simulations, the output does not always match what telescopes record. The web that exists in observation and the web that exists in models are not the same web. Somewhere in the formation process, data is missing. To understand what is missing, it helps to understand what entropy increase means in a cosmological context. Entropy is the tendency of physical systems to evolve from ordered states toward disordered ones. On small scales, a gas expanding into a vacuum, a hot object cooling, entropy increase is observable and measurable. On cosmic scales, the relationship between entropy and structure is less direct. Gravity complicates everything. Gravity is an attractive force, and it causes matter to clump together. Clumping is, in a local sense, the opposite of disorder. But on the largest scales, as the universe expands, the overall entropy of the system is increasing. The cosmic web is a product of this tension between gravitational attraction pulling matter into structure and the thermodynamic expansion of the universe, driving matter apart. What the models predict is that this tension should produce a specific outcome, a web that reflects the initial density fluctuations, amplified by gravity over time, shaped by the distribution of dark matter, and smoothed by the pressure of ordinary baryonic matter. Simulations like the Millennium Simulation and Illustris TNG have reproduced web-like structures that resemble what is observed. The broad features match, but the match is not precise. And in cosmology, the gap between broad resemblance and precise agreement is where real science lives. Precise agreement requires precise data. Precise data requires knowing exactly what is in the universe and where it is. The first missing layer is dark matter. Current models estimate that dark matter constitutes roughly 27% of the total energy content of the universe. The cosmic web, in its current state, is understood to be primarily shaped by dark matter filaments. Ordinary matter, the gas, the stars, the galaxies, falls into the gravitational wells created by dark matter structure. But dark matter has never been directly detected. Its distribution is inferred from the behavior of visible matter. The map of dark matter that underlies the cosmic web is not measured. It is reconstructed, and the reconstruction depends on assumptions that may not be complete. The second missing layer is baryonic physics at large scales. Ordinary matter does not behave as a simple tracer of dark matter. Gas can be heated, ejected, redistributed by feedback from supernovae, from active galactic nuclei, from processes that occur at the level of individual galaxies. These processes are small relative to the scale of the cosmic web, but their cumulative effect over billions of years may have altered the distribution of matter in ways that current models underestimate. No simulation can resolve both scales simultaneously. To model the cosmic web at universal scale, simulations must average over the behavior of individual galaxies. To model individual galaxies accurately, simulations must zoom in so far that the cosmic scale becomes unreachable. Both cannot be done at once with current computational capacity. Every simulation of the cosmic web carries inside it a set of approximations, subgrid physics, parameterized feedback, smoothed baryonic behavior that cannot be fully validated. The formation history of the cosmic web has never been completely reconstructed from first principles. The third missing layer is observational. The cosmic web is not directly visible. Individual galaxies are visible. Galaxy clusters are detectable through X-ray emission and gravitational lensing. But the filaments that connect them, the structural skeleton of the web, are largely invisible. They contain gas at temperatures between 10,000 and 10 million Kelvin, known as the warm-hot intergalactic medium, or WIM. This gas does not emit light strongly enough to be mapped easily. It absorbs certain wavelengths of ultraviolet and X-ray light from background sources, producing faint spectral signatures. Only a fraction of the expected WIM has been observationally confirmed. The rest is predicted to exist, but has not been seen. Roughly 40 to 50% of the ordinary matter in the universe is currently unaccounted for in direct observation. This is not a minor calibration issue. This is the structural material of the largest objects in existence, and it remains partially invisible to every instrument currently operating. The filaments of the cosmic web are built partly from matter that telescopes cannot reliably detect. Every measurement of the web's shape, its density, its coherence, is a measurement made through a gap. When cosmologists attempt to measure the statistical properties of the cosmic web, the power spectrum of matter fluctuations, the correlation functions of galaxy positions, they find values that are close to predictions, but not perfectly aligned. One persistent tension involves the parameter sigma 8, which measures the amplitude of matter clustering. Measurements derived from the distribution of galaxies and from the cosmic microwave background do not always converge on the same value. The discrepancy is not large enough to disprove the standard model of cosmology. It is large enough to suggest something is not fully accounted for. Something in the formation history of large-scale structure may not be in the model. Whether that something is a property of dark matter, perhaps it is not perfectly cold. Perhaps it has a small interaction cross-section that slightly smooths structure, or a property of dark energy, or a gap in the treatment of baryonic feedback, or something else entirely, is not currently resolved. Each possibility has been explored. Each has limitations. None has closed the discrepancy. The web is there. Its broad form matches predictions, but the precision match fails, and the reason it fails cannot yet be isolated. There are observational programs that may, in time, reduce some of the uncertainty. The Euclid telescope, launched in 2023, is designed to map the large-scale structure of the universe across billions of light years, measuring weak gravitational lensing and galaxy clustering with a precision that previous surveys could not reach. The DESI survey is building a three-dimensional map of galaxy positions across an enormous volume of the observable universe. The square-kilometer array, when fully operational, may detect radio emission from filamentary gas with unprecedented sensitivity. What these instruments can do is sharpen the picture. What they cannot do is recover the data from epochs that cannot be directly observed. The formation of the cosmic web began in the first billion years after the Big Bang. The density fluctuations that seeded it were established even earlier, in the first fractions of a second. The chain of processes that led from those initial conditions to the web that exists today passed through phases that left no directly recoverable record. Ionization altered the state of intergalactic gas in ways that affected structure formation. The epoch of first star formation set conditions that propagated forward. Each transition introduced variables that compounded into the present structure. The web is the product of a history that cannot be fully read backward. Within this uncertainty, one question remains structurally open. Why is the web as organized as it is? The level of coherence in the filamentary network, the way structures align across distances that should have been causally disconnected in the early universe, is consistent with models, but only barely, and only under specific assumptions about the initial conditions. If those initial conditions were slightly different, the web would look different. The fact that it looks the way it does constrains the initial conditions, but it does not uniquely determine them. Multiple configurations of the early universe could, in principle, produce a web that matches current observations within measurement uncertainty. The observed web does not uniquely solve for its own origin. What can be said is this: the cosmic web formed through a process of entropy increase, acting on an initially seeded, gravitationally unstable system. The mechanism is understood in outline. The details that would allow a complete reconstruction of the formation history are not available. The missing matter in the filaments has not been fully mapped. The subgrid physics that governed how galaxies fed back into their large-scale environment has not been fully constrained. The tension between different measurements of clustering amplitude has not been resolved. The web exists at a scale that makes complete empirical coverage impossible with current instruments. New surveys will improve the maps. Better simulations will sharpen the predictions. Some of the current gaps will narrow. But the formation of the largest coherent structure in the observable universe, the filamentary network that defines the shape of everything, was shaped by processes and initial conditions that left only partial traces. What remains after every current measurement is accounted for is a structure whose coherence slightly exceeds what can be fully explained by the data available to explain it. The cosmic web is the universe's largest pattern. The data needed to fully account for it does not yet exist.